Hello, my name's Peter Shields, and on behalf of ANYmal Scientific, I'm excited to welcome you to today's webinar, Surveillance and First Response with the Legged Robot ANYmal, to be presented by Dr. Péter Fankhauser, the Chief Business Development Officer and co-founder of Zurich-based startup company ANYbotics. ANYbotics, a leader in the development of highly sophisticated autonomous mobile robot solutions for harsh and challenging environments. I'm sure you'll find today's presentation of this exciting new technology very interesting. So over to you, Peter.
Great. Thanks a lot, Peter. Thanks a lot for hosting us today. I'm very excited to present you some of the work that we have been doing, and I think it's very exciting to talk about the topic of legged robots here. Now, I also want to set the expectations right. So after these presentations, you won't be able to order a robot and deploy it in your everyday work just yet, but I want to show you a little bit about the technical state-of-the-art, about the possibilities that open up with legged robots and surveillance and first response. And then I want to talk about how we can take the current state-of-the-art and look ahead at the path forward, how in the future we can reach these goals in deploying these robots. Now, I want to start by saying, and I think all of us can agree, that robots are changing the way we work. We have seen that 40 years ago in manufacturing, when Ford started using robots in their facilities to automate the manufacturing of cars. And if you buy a car today, you see that large parts of it are built actually by robots. In 2010, Amazon started using logistics robots in their facilities. When they're driving around, they automate the process and make it much more efficient in their warehouses. Now, if you look at these two types of robots, a manufacturing robot is typically inside a cage, is bolted down and in this special environment where it doesn't share the space with humans. And in logistics, we find also these warehouses, there have been special built for robots. There might be lines on the floor, or there's beacons around to guide the robots in their work. Now, the logical next step is to take out these robots into everyday environments. Here we find a vast new applications, and this can be in industrial environments, urban environments, or natural environments. And here, the motivation to use legs is very clear, because an environment is typically built for humans, or natural environments. We can see it with animals, that they can move around very gracefully with the use of legs. Now, for the last couple of years, we have been field testing legged robots for all kinds of different applications. And here's an overview where you see the robot can be used for industrial inspection, for the inspection of utilities, in agriculture, or even last mile delivery. But today I want to talk about the fields of surveillance and patrolling at once, and about the field of first response. And I think these two are somewhat connected, because we're in the field of surveillance and patrolling. It's all about preventing potential dangers by finding problems as early as possible. Whereas in first response, it's all about moving in after something had happened, and to solve the problem, or helping in solving the problem as quickly as possible. Now, if you look at the task of surveillance and patrolling, I think the main challenges of it today is that if you want to extensively cover either with patrolling with people, with cameras, or other types of sensors, the costs become very high. There's certain non-perceptible dangers, such as a person would not be able to smell certain gases, or electricity is not visible to us directly. And then even if we deploy sensors or cameras, they still rely often on the manual interpretation of the footage and the data. Whereas in first response, the main challenges are to minimize the delay between the alarm and the operation. And our first response team are often faced with uncertain situations. And now moving in, often they put the dangers into life, and this is, I guess, in general, problem to make sure that the first response team can act as safely as possible. Now, if you look at these two fields, surveillance and patrolling, and first response, I want to show you the connection between these two fields. Now, diving in for surveillance and patrolling, it's all about environmental monitoring and status reporting. So robot going around and capturing all of this data all by itself. A robot can do this automated, it can do it frequent, and the robot doesn't get tired. It's very accurate and enduring. And we design our systems such that they're navigatable on all different areas, such that, so we say all walkable areas, everywhere where a human can go, this robot will be able to go. And our goal is that the environment will not have to be adapted to the robot, but rather the robot is capable enough to go everywhere where humans can go. Now, in first response, it's about the fast first response. And if you have a robot in place, the robot can already move in because it's already deployed as a surveillance robot and now being able to act as a first response robot. With a remote operation, we can control the robot at a safe distance without putting people into harm's way. Now, the robot carries a bunch of sensors, and I'll show them to you in a second, but it's all about not only cameras, but also hearing the sound, seeing temperatures with a thermal camera, gas detection sensors, so having all these multi-model sensors to have a very good situational assessment. And finally, the robot, these situations don't happen always in sunshine, so the robot is built that it's all weatherproof, it's water and dust proof, and all the sensors, they work in darkness and in bright sunlight. Now, looking at these two fields, I want to show you a little bit the connection, how from one type of work, the robot can move into the other type of work. Now, for surveillance and patrolling, we set the robot out to work autonomously, so it autonomously navigates through the environments, but it does so in fixed routes that have been taught the robot before. And all the incoming data the robot processes inside its computational brains, and so it can take the data, interpret it, and trigger an alarm if necessary. Now, all of this can happen autonomously, and if there's any unusual situation, it can trigger an alarm, and then typically we can take over as an operator. And the operator can control the robot, or control the sensors, the cameras, where they should look at. Now we're not restricted to any fixed route, and the operator is able to let the robot move anywhere he pleases to do so. And finally, since there's a human now in the loop, we can take all the cognitive capabilities to interpret the situation, assess the risk, and then take decisions based on that data. Now, we design our robots to be able to very quickly move from this autonomous surveillance and patrolling mode into this first response mode. So at any moment of time, if this robot has signal, the operator can take over and then switch to this teleoperated control. So we have a very quick and transparent way to switch from autonomous to remote controlled mode of the robot. Now, like I said, we have been field testing this robot for the last couple of years, and I will show you some situations exemplary and show you a little bit the features of our robot. So the robot is designed to be able to move on any surface. On a flat ground, it can run up to the speed of roughly human walking. But then the legs become really advantageous when going up difficult terrain, such as a sandy slope through grass, or then climbing over obstacles. And due to the four-legged system, even very slippery situations, such as these icy stairs, can be maneuvered very robustly. The robot can carry up to 5 to 10 kilogram in payload, and here we deployed it with an inspection head for industrial inspection, where it goes around all by itself and then reads off these pressure gauges or lever position, and not only takes a picture, but is also able to interpret the image. The robot is ruggedized, water and dust proof, and so we can deploy it in all various situations and put it into hard to reach places. All the intelligence and navigation happens on board the robot without any data connection. And here we see an example how the robot interprets the environment and then plans its motion to climb over this difficult terrain. And even if a foot gets stuck, the entire locomotion pipeline is set up that it can untangle itself through these difficult situations. As a remote controller, you see a camera feed, but also a 3D reconstruction of the environment to help you to orient yourself in the room. The battery lasts for 2 to 3 hours, and in autonomous mode, the robot can all by itself go back to a docking station and charge itself. Now, what's special about the robot ANYmal is that it can rotate its legs completely around, such that this relatively small robot can climb over big obstacles, or even change its morphology to crawl underneath objects or into pipes. And then lastly, we can use the legs to even do simple manipulations, such as pushing an object or pushing a button. Now, looking at our platform, it all starts with the extreme mobility that the legged locomotion allows the robot to do. The robot, like I said, is water and dust proof, and all the computation happens on board the robot with an extended battery life. We have front and back stereo cameras to detect the terrain and plan a safe motion over the obstacles. And for the entire environment perception, it uses a LiDAR similar to the ones that use an autonomous car to localize itself in its environment and to create scans such that the human can interpret them in the map. Now, this is the basic platform, and it also features a speaker and a microphone such that you can remotely communicate with any person in the field. This is the basic platform, and we also deploy it here as an example with a inspection head, where in this case we have a pen tilt unit, where we have a visual camera, a thermal camera, and a very sensitive microphone. And this is a modular payload, can be extended or switched to another payload as necessary. Now, for the current perception capabilities, the robot, as I mentioned, can go around and take images and interpret them. We can do thermal inspection, and even from distance without touching, the robot can measure temperature and detect hotspots. We can do audio inspection by checking what is the regular noise of a machine, what is the regular sound of the environment, and is there any unusual activity in this environment, and to trigger an alarm. As a byproduct of the robot's navigation capabilities, the user can access these 3D maps also in post-processing to assess the structure of environments. We use computer vision and then AI to do object detection in the scene, such that we can check for safety relevant features, such as, is the fire extinguisher there where it's supposed to be, or are there people where they're not supposed to be? And using gas detection sensors, we can give the robot a sense of smell, even for gases that are inconceivable for humans. Now, these are 6 examples that we have already field tested, but of course, it's up to the user to extend the robot or tell us how to extend the robot with the sensors necessary in the field. Now, I want to talk a little bit about the different operation modes of the robot and how, looking at more in the detail, how they affect the navigation and the bandwidth that is required. Starting for teleoperation, the command is sent through a joystick, and typically are velocities of the robot. So the person is directly in control of the motion of the robot, but the robot coordinates all the leg motion and balancing to maneuver through the environment and over obstacles. The user gets feedback via a video feed. It can look at the thermal images, it can listen to the audio, and look at the reconstructed 3D environmental map. Now, since there's a lot of data going back and forth and the human is really in control, this requires a rather high bandwidth and low latency data connection. And currently, we have a Wi-Fi option, and soon we'll also work with 4G and LTE. Now, if the connection is a little worse, we can also give the robot a mode between teleoperated and fully autonomous, and this is what we call supervised. So here, instead of sending direct velocities to robot, we send robot rather goal position and tell robot, please go there, or direct this sensor into this direction. And we can do this easily via a computer user interface. Then the robot uses all its sensors and intelligence to safely navigate to that goal while avoiding obstacles. Here we get the same amount of feedback if we have the bandwidth, similar to as in teleop, so all the video and thermal images and acoustics. Now, since the robot here has taken over some of the navigation capabilities. This requires a lower bandwidth, and the latency can be much higher because the robot is reacting all by itself. Now, in going all the way to the autonomous mode, here we typically control the robot in what we call a teach and repeat fashion. So once the robot is guided around through the environment and told what to check for. And then once it's been taught, the robot all by itself can execute this mission. And it's smart about obstacles. It goes around, and even if, let's say, a door is completely blocked or a pathway is blocked, it's smart enough to find an alternative path to fulfill its mission, because initially it's been taught the environment and it's aware of all the routes that lead to the same goal. Similarly to the previously two mentioned operation modes, we get full feedback on all the sensors if there's a data connection. However, the robot can even work now without any wireless data connection in really remote places, since it's gathering all this information, and once it goes back to an area where there's data, it can offload this information to the user and to the protocols. Now I want to show you two examples, one for the teleoperated mode and one for the fully autonomous mode, and how we have been field testing ANYmal. For the remote control mode, this is a typical user interface as we use it on ANYmal. In the center, there's a 3D environment, and here we show actually a CAD reconstruction of the environment if available, or it will be a point cloud if we scan it during the autonomous mission. Then on the left-hand side, we have the situational wide-angle camera. It gives you a good idea of how does the environment look like, where does the robot is in relation with the environment. And then what is nice, if we have, for example, a zoom camera as a payload, we can say on the left-hand side, click on one of the options, one of the interesting points, and then let the robot all by itself zoom to that point and give us a really high resolution picture, even for remote places and objects. On the bottom, we see all about the mission, the protocol, what has the robot been doing, and what is it about to do. And then on the bottom, we have a bunch of modules, which I won't be able to go into detail, but it's all about the control of the robot and potentially setting up special actions or autonomous missions. And then on the right-hand side, it's all about the robot itself, what is the health of the robot, what's the battery status, etc., and any errors that might have occurred during this operation. Now, in the following video, the robot is directly teleoperated by a person, and here we have a wide-angle camera in the front and the thermal camera, and additionally for dark environments, this flashlight. So on the lower left, you see an online reconstruction as the user sees it when controlling the robot. So this helps it to assess, should I go quickly here, should I go lower, and then the robot balances and takes all the footsteps all by itself to climb over these steps. And here's an example of how the onboard camera the impression in darkness with the light together, and how the user sees the environment in front of the robot. Now, when faced with difficult obstacles, such as this ledge, we can again switch to a special maneuver mode, and then let the robot figure out or help it in climbing over these difficult terrains, such as here, turning the legs around to increase the height of the robot to be able to climb over this step. And then you see an example of the thermal camera here, where in the picture it's very easy to detect a person due to its heat. After the mission is done, or during the mission, you see the reconstruction, and you can tell how does the environment look like, what changed compared to the original plan. And this gives rescuer a great idea of the space inside, and it's really good to send in then, based on this knowledge, to send in the team and let them help people in need directly and easily and safely. Now, for the next example, we have deployed ANYmal on a offshore wind energy farm for fully autonomous inspection rounds. So here again, we see the inspection head with the thermal camera and the zoom camera and microphones. And initially, we walk around with the robot and teach it all the environment and we show it what it is supposed to do. And here you can see how it reconstructs this environment and then knows how can I access these different rooms. And then essentially we press the play button and the robot can robustly repeat these missions. You see the images coming in, it takes these pictures and interprets them and puts them in the protocol. And you see in the lower right corner how the robot is currently located and how it localizes with respect to the environment. So it knows its position to a sub-centimeter accuracy even in very large environments. On the lower left, you see how the robot in real time creates a map of the obstacles in front of it, and then is smart enough to either go around the obstacle, climb over the obstacle if possible, or to find an alternative route if the entire pathway is blocked. And then, of course, we often find in this building that there are stairs, and this is really where legged robots excel at in climbing over this difficult terrain. Now, we often get asked, there's drones, there's tracked vehicles, so why should we go through the complexity of using legs? And I will show you some data based on this table. Now, for tracked vehicles, they're clear they can carry a lot of payload, they're very robust, and their operation time, their battery lasts for hours and hours. But the problem with tracked vehicles, once you want to go in and climb difficult terrain or even stairs, these vehicles become very bulky and big, and hence they're less suited to go into narrow spaces. So we have to trade off here with these robots. Whereas with drones, they're very versatile and can fly to have a good vantage point very quickly. And we all know that the payload for drones is very limited when they have a reasonable size. And also the operation time for a typical drone is maybe 15 to 20 minutes. And there's certain limitations in the turbulence and when you have dust on the floor, the noise, and even the safety with these vehicles. Now with the legged robot, we can combine these two worlds. We have a platform that can carry a lot. It has a high operation time, but at the same time, a small robot like ANYmal is still very capable of going over rough terrain and even climb very steep stairs. So while tracked vehicles and drones have all their advantages, I think for a lot of applications, such as patrolling, search and rescue, and first response, we have a platform that combines the best of the two worlds. To give you a little bit background on our work, we're actually a spin-off company from the Technical University in Zurich, and we have 10 years of research, been doing 10 years of research in legged locomotion since 2009. We started off with early demonstrators and then took the robot and the demonstrators, adding them autonomy, performance, and robustness, but coming from demonstration now into application, where we founded our company 2 years ago. We have been field testing the robot for different applications for the last couple of years, also a lot of in industrial environments, but also going into sewage system. It's about railway inspection, oil and gas projects, and similar. We also have been working this year with last mile delivery. So our goal is to really broaden the applications and then look at all these fields, and this helps us to develop the product further. Right now, the ANYmal prototype is in a technology readiness level 7, and our next generations will continue to improve in the maturity of this product with the goal such that we can launch a product by 2020 or 21. Now, just because ANYmal is a prototype, it doesn't mean it cannot be used just yet. So what we like to do is go out to work with companies and implement a robot in the field in terms of a feasibility study or a pilot project. And this could work as follows. First, we would talk to the customer and talk about the tasks that are required in the field. Let's talk about the environmental conditions and then come up with a schedule and a milestone on how we should test this robot in the field. And any preparations that need to go, we would do in our labs in preparing the robots for the task. At the second stage, we can go to the customer and really implement it in the field and test it. And this can be in functional tests, in field tests, and going out to robot and also getting the feedback from the staff there is a very valuable component of these tests. In third, we will do a full coverage with a report, but also creating videos to really get people the impression on how does the system work in the field. We then go about analyzing what was working, what was not working, and do a gap analysis. And take all of this information together with the customer to define what is the business impact, how is this going to scale with the customer. Now, after such a pilot project, we can go where the requirements fulfilled. If no, we should start another project, or if yes, we get one step closer, ready for commercial application. This is our team. We're about soon 30 people and still growing. And we're lucky to say that our company is still fully in the hands of the original founders, also thanks to these general institutions on the right-hand side. With that, I'm at the end of the presentation, and I would urge you to follow our social media channels where we always update our progress, and we also have a newsletter where you can sign up to get up to date on our developments. Now, you all going to have questions, and I've been also sent a couple of questions beforehand per email. So I'll go through all of those questions, and then I'm happy to take your questions as you type them in. Peter, is it okay if I go ahead, or
yeah, it's fine to go ahead.
That you go in between?
We haven't got any questions yet, but I know you've got some that were sent previously. So if anyone does have any questions, please just type them into the question box, and Peter can answer these ones first. Thanks.
Okay. So the question is about a very important topic, especially in remote control. What's the working range, and at what point does the operator lose connection? Right now, we use a standard Wi-Fi system, meaning that in direct line of sight, Wi-Fi would typically work from 50 to 100 meters. And if there's walls, especially thick walls, this deteriorates very, very quickly. So this is not the ideal solution if you want to go really deep. And there's alternative solutions that we've been trying out, from point-to-point or mesh networks. But I think one of the alternatives is really in environments, in urban environments, to go what we're going to be able to provide in the future for 4G and LTE, where wherever you have a reception with your phone, you're going to can control the robot even over very large distances. The question if the unit can be decontaminated if it's exposed to chemicals or dust. I'm not an expert in chemical decontamination, but the robot is IP67 waterproof and dustproof, meaning that essentially we can hose it down, submerge it, and really get the dirt and potential chemicals away from the system. The question is if there's a protective cover that could be used while in operation. Now, we don't have any cover like that. Of course, that would be could be done, but at the same time, I'm not sure if it's really needed, since the robot is IP67 water and dust proof. And we'll have to see if based on the requirements, if this is actually really required, or if the current specifications already solve this problem. What would be the maximum temperature if it were exposed, to example, in a burning building? Right now, the robot is specified up to temperature of maximum 40 degrees, and I think like minus 10 degrees. But looking at the maximum temperature, I would not suggest it right now to send it in a burning building, just due to the electronics and those things will probably not withstand the heat. So right now, the robot is not built to send it into a burning building. But at the same time, in the future, we might think of a protective cover that might reflect some of that heat for a short-time basis. The question about the capacity of the thermal image camera. So right now, the sensor that we deploy, and of course this is modular, the thermal camera can detect temperatures from minus 20 degrees Celsius up to 900 degrees Celsius, with the option to go higher up to 1,500 degrees Celsius. Now, how easy is it to operate ANYmal, and what training is required? As I said at the beginning, ANYmal is still a prototype and not ready to be deployed on a day-to-day basis. However, The robot, as you've seen in the user interface, it is not very complex to use, but it still requires some training. Since typically we go out and implement it in the field, currently it's only our team being trained to do this, but in the future we foresee that the robot will be even easier to be used, and then the adequate training will be provided. Will the robot come as a standard kit and then optioned up to suit the application? Right now, you can buy an ANYmal prototype from us, essentially, and we have sold a bunch of robots to universities, and they are adding their own sensors, their own capabilities on top. Now, we foresee that we'll be doing both, selling the robot as a standard kit and leave to the customer to implement the option, or work with us and we'll have different versions of the robot designed for different applications, and then being sold directly to the customer without the need of having an engineering department at the customer site. Hazardous area classification is a very important topic to us, since especially in the oil and gas, we get often asked about explosive environments. Now, whereas the current ANYmal robot is not certified to any hazardous area classifications, we are working on a version that will be EX explosion proof for zone 2. Is there ability to assess a point of no return to aid in retrieving of the unit? This is a very good idea, and to answer that question, we have a version you can see the battery state, so meaning that the robot will be able to tell you how far has it gone and at what point will the battery not last to go the same route back. But this is all the intelligence it has right now. It's not smart enough to say, if I climb down here, I won't be able to get up, similar things to that. So this is a very important point, and we'll sure to address this in our future development.
Thanks very much, everyone, for attending today. Thank you, Peter, for your time today. Very informative and interesting presentation on some amazing technology. So thanks very much.
Thanks a lot for having me.